Hi everybody, welcome back to Super Awesome Calculus. I'm Augie Kennedy, and today we're still on Chapter 4, which is entitled Everything is Derivative. And last time we went over curve sketching and how to use derivatives and all of the things we've learned so far in the course to sketch a graph of any function. Today we're going to do something that causes unlimited consternation amongst almost all calculus students, and that is the idea of optimization. But we're going to find that it's actually pretty easy to do, and it's just going to use maximum and minimum value techniques that we've learned in the past. But before we do that, let's go over the sketch that I gave you last time. I asked you to sketch this curve. Y equals square root of 1 minus x squared over x. That was the function I asked you to sketch. Now, it would take me probably most of the 25 minutes I could have here to go over that problem. So instead, I'm going to go over a few key points. First of all, f of x, let me draw it again, is square root 1 minus x squared over x. The domain is defined whenever this is not 0 and whenever that is not positive. So we have domain restrictions in both the numerator and denominator. We need 1 minus x squared to be greater than 0. As long as that happens, we're good. Also, as far as the, which of course only happens over a very short period of time between 1 and -1, and not 0. The intercepts, we can plug in y of 0, we don't get something, no y-intercept. We can set the x, and we can find out that the x-intercepts are at 1 and -1. So it's going to touch x at 1 and -1, but it's not going to touch the y-intercept, or the y-axis, because that's undefined. As far as whether it's even or odd, we can plug f of -x here, and we're going to get this whole function, but negative. And that means that f of x equals negative f of x, which means it's odd. My nose is really itchy, I'm sorry. So the function is odd. Now, what else do we know? We know that we can check for vertical asymptotes and horizontal asymptotes. If you check the limit, you'll find that the limit is undefined as x approaches infinity, and we'll find that there is in fact a vertical asymptote at x equals 0, or at y equals 0. So we have no horizontal asymptotes and we have a vertical asymptote. Then you can go for the increasing and decreasing tests. F prime x, you should have gotten negative, is that a 4? I can never even tell my own handwriting sometimes. I believe it's -4. That might be a 1. X squared times square root 1 minus x squared. And then the second derivative is going to be 2 minus 3x over x cubed 1 minus x squared times the square root 1 minus x squared. Now, about the first derivative, we can see that the first derivative is going to be decreasing between -1 and 1. But that's wherever the function is defined. So basically, the function is going to be decreasing everywhere. So there's not going to be a minimum, there's not going to be a maximum, it's just going to be decreasing. So it's decreasing, and using the second function, we can realize that there is in fact going to be an inflection point. And if you actually solve this, you'll find that the inflection point is at square root of 2/3. Now what you do is you take that plus and minus. You take those 2 points, square root of 2/3, and you plug it back into the original function to find out what the y value would be. And the y value turns out to be plus and minus square root of 1/2. So those are your inflection points. Going from concave up in the center near the y-axis, or axis, wait. It's going to be concave up after, from negative 2/3 to negative 1, and it's going to be concave down from 2/3 to 1. Yeah, square root of 2/3 to 1. So, with all of that information, we can draw the curve, and hopefully you ended up getting something that looked kind of, sort of like this. 1, -1, negative square root 2/3, square root 2/3, vertical asymptote at 0, and we have that, like that. And that should be your, you got your intercepts here, and that should be what the graph looks like somewhat. So, that takes care of the big problem from last time, and now we can talk about optimization. So, optimization. You've probably been exposed to these kinds of questions before. You have X amount of material. How do you optimize it? Well, really what you're asking yourself is, what is the absolute maximum or the absolute minimum shape or size that I can get out of this material? And when we do that, we're looking at derivatives. It might not seem like it, but that's what we're asking. Let's take this example. I'm going to read. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. So what are the dimensions of the field that has the largest area? Step 1, what am I asking? That's what you've got to know first with an optimization problem. I said the farmer has 2,400 feet of fencing and wants to fence a rectangular field that borders a river, needs no fence along the river. What are the dimensions of the field with the largest area? It sounds like I'm given a bunch of material, I need to find a maximum area. Good. Second step, let's draw. Okay, so we've got a river, that's our river, and he's going to have to make a rectangular type thing. It doesn't matter if you draw it square or flatter, just as long as you have the notation. So there's our river, and there's the box, and he's got 2,400 feet of fencing. I mean, this could be 100, 100, 2,200. I mean, it could be, he's got 2,400 feet of fencing. He could do 1,000, 700, 700, and you could keep plugging these in until you get the right answer, but there's a more efficient way of doing it. All right, so we've drawn this. What we're looking for then is we're looking for area. Well, let's call this side X, and this side Y. Because, you know, two of the sides are good. We're not making a triangle here, we're making a rectangle, so two sides are going to be equal, and then there's going to be a long side, Y, or a short side, depending on the values of X. That'll give us the best area. So area is going to equal X times Y. That's what area of a rectangle is. XY. Now, what do we know? Well, we know that we have x, 2x, x plus y, 2x plus y equals 2,400. 2,400 feet. We've got 2,400 feet to build one side, two sides, three side. 2 of x plus y equals 2,400. With me so far? Good. Okay, now, once we have that, what we can do here is we can find y in terms of x. Why would we want to do that? Well, because this isn't multivariable calculus. You don't need to work with both x and y, not when we can find out what x is in terms of y. So let's go ahead and set it up. If 2x plus y equals 2,400, then it stands to reason that y equals 2,400 minus 2x, right? Yeah. So really, we're not looking for a equals xy anymore. Now we're looking for the area of x times 2,400 minus 2x. Now we're really in business. All right, so let's erase a little bit of this. Because now we have an explicit formula of what we're looking for. We are looking for some number. And the number, the beauty with optimization problems is that the number will almost magically appear to you. X times 2400 minus 2x. It's the same as xy, we just have an explicit version of y here. So, in terms of x. So let's go ahead and let's multiply through. A equals 2400x minus 2x squared. We've got the area. That's the area. Now what do we want to do? Well, this is an optimization, and this has to do with derivatives. So really, there's only one thing to do. And you probably would have guessed to do this. We're going to take the derivative of A. If area equals that, what's the derivative of that? Well, it's going to be 2400x is 2400 minus 4x. Boom. There you go. Now, in order to do an optimization problem correctly, we need to find a minimum or a maximum, which means we're looking for critical points. And a critical point occurs when the derivative is, that's right, 0 equals 2400 minus 4x is the same as 4x equals 2400. And that happens at only one spot, and that is 4x, 2400, x equals 600. Ta-da! X equals 600. What does that mean? Well, that means that at x equals 600, the derivative is 0, which means it's a horizontal tangent line on the function of the various shapes you can have. So therefore, 600 is what x should be. But we're not quite done yet. We're not quite done. What you can do, you can check if that's a maximum or a minimum, or you can just know. Sometimes it's very logical whether it's a maximum or a minimum. But if you want to, you can do the second derivative test and realize that it fits along the lines, because it's always going to be -4. You're going to have always concave down, which means that's going to be a maximum. And sure enough, 600 is a maximum. So what does that mean? That means 600 equals x. Alright, now that means 2x plus y equaled 2400. Okay, that's fine. Let's go ahead and plug this in. If y equals 2400 minus 2x, well, then y equals 2400 minus 1200, 2x. So x equals 600, y equals 1200. Meaning that this y, this side must be 1200 feet long, this side must be 600 feet long, and this side must be 600 feet long. And that is the largest possible area that you can have. And that is how to do an optimization problem. You can do this with cans. My old professor loved to put like cylindrical cans and other weird shapes, like I gave you that window with the semicircle on top of it. You can do all of these things with that. You just need to know what you have. Like here, the key observation was, okay, we're given a perimeter, we want to find area. Let's relate area to perimeter, kind of like a related rates problem. Relate area to perimeter, take the derivative, set it equal to, get down to one variable, take the derivative, set it equal to 0, and then plug everything back in and see what you get. So, once again, know the problem, find out what you're being asked, know what you have. Do you have perimeter? Do you have area? Do you have volume? Do you have, what do you have? Write down what you have, write down what you need to know. Relate the two to each other, get down to one variable, the way we did here, by putting y explicitly in terms of x. You will be able to with these questions. And then once you've done that, go ahead and take the derivative, set it equal to 0 to find whether it's a maximum or a minimum, and then go ahead and plug everything back in. There you go. Now, there's one more thing, one more example I'd like to do, and that's an economics/business example, which is really nice if you want to make a lot of money or make your boss really happy one day. A couple things to know ahead of time. First, we have C of x. That's the cost function. C of x equals cost. All right? Then we have R of x. This is called the revenue function. This is x, how many units, times P of x, which is the price. So P of x is little p of x equals price. R of x equals revenue. And this makes sense. Revenue equals the amount of things times the price it costs to sell them. Finally, the last function is big P of x, profit, equals R of x, revenue, minus C of x, cost. Profit equals revenue minus cost. Very intuitive. You already knew this. You probably knew this in 2nd grade. All right, now, some of you didn't know how to say it, but I bet you knew it. So, that's our function. Here's the question. A store has been selling 200 DVD burners a week at $350 each. A market survey indicates that for each $10 rebate offered to buyers, the number of units sold will increase by 20 a week. Find the demand function and the revenue function. How large a rebate should the store offer to maximize its revenue? Okay, this is pretty good and pretty easy. So these are the functions we're working with. C of x, the two real keys here are R of x equals x little p of x, and big P, profit, equals R of x minus C of x. Knowing that, we know that the store has been selling 200 DVD burners a week, 200 DVD burners, 200 DVD, I'll just call it, at $350 each. Okay? A survey indicated that for each $10 rebate, resulted in an increase of 20 DVDs. So, the question is, how large a rebate should this store offer in order to make as much money as it can? If each $10 rebate jacks it up, what happens? Alright, now the way you figure this out, let's call X the number of DVD burners sold every week. Okay? Then every increase in sales is X minus 200. You with me? Okay. That means that for each increase of 20 units sold, the price is decreased by $10. That's pretty obvious. $10 rebate, lower price, more DVDs. Okay. So, each individual unit, we can write that as 120 times 10. So therefore, the demand function is P of x, little p, equals 350 minus 10 over 20, which is 1/2. All right, times x minus 200. There you go. Which, if you do the math there and distribute that through, you'll get 450 minus 1/2 x squared. That's your demand function. 350 or 450 minus 1/2 x squared, which is derived from these numbers here. The 350 that you start with and the effect of the rebate on the cost of the DVDs. So that is, we've got the demand function, P of x equals 450 minus x squared over 2. Okay? Now, the revenue function we already know is r of x. Well, if P of x, big P of x equals r of x minus c of x, well then it would stand to reason that r of x is xpx, so that's going to be x times P of x, so we know P of x, so r of x is going to be x times 450 minus x squared over 2, or the revenue function is 450x minus x cubed over 2. Right? No, I'm wrong. It's P of x is x over 2. Yeah, r of x is going to be x squared over 2. My bad. I should probably quit while I'm ahead. Or behind, whatever. The P of x is x over 2. It's not x squared over 2. I have no idea why I wrote x squared. Anyway, r of x is 450x minus x squared. We know what to do here. We're going to minimize or maximize revenue. So we're going to take the derivative. It's 450 minus x squared over 2 is going to be 2x over 2, which is going to be x. Right? Yep, 450 minus x. So we're getting close now. We have the derivative of the revenue function. Let's go ahead. If r prime x is 450 minus x, let's set it equal to 0. 0 equals 450 minus x. Pretty easy to see. X equals 450. But what does that mean? Well, if we use the second derivative test of this function, we know that that's a negative. It's always going to be negative 1. So negative 1 is always going to be concave down. So we're looking at an absolute maximum. So there we go. If P of 450 then, because P of x is the demand function, P of 450 is 450 minus 1/2 times 450, or 225. So, if the rebate, therefore the rebate is going to be 350 minus 225, or 125 is the ideal rebate. I completely butchered that problem, but it's just another way to see how optimization can work. The optimization question I gave you is much more like the first one. So here's the optimization problem for you guys to work on today. Consider the following problem. A farmer with 750 feet of fencing wants to enclose a rectangular area and divide it into 4 pens with fencing parallel to one side of the rectangle. What is the total possible area of the 4 pens? Remember, find out what I'm asking, find out what I've given you, and draw it. I don't care if you suck at art. Just draw it so you have an idea of what exactly it is you're working with. Go ahead, remove one variable, take the derivative, set it equal to 0, maximum or minimum, it'll be a maximum, and go ahead and find out your answer. So, there you go. Thank you very much for coming by. One more chapter, I believe, or one more section of this chapter, and then it's test time. So, have a great night or day or whatever time it is, and take care, y'all. Bye-bye.